right? So we're going to prove the Rados theorem, which states that the system AX equals 0 is regular on N, which means that no matter how I color the set of positive integers with finitely many colors, there exists a monochromatic solution. So this is regular if and only if the matrix A satisfies the columns condition. And let me remind you the columns condition. So the matrix A satisfies columns condition if you can partition the set of columns into subsets, so that the first sum of the first columns is 0, sum of the second column is spanned by the column vectors in the first set with the rational coefficients. Set of columns in, the sum of the column vectors in the third part is spanned by set of column vectors in the first and second, etc. So set of columns in T's part is in the span of the set of span of the column vectors in the first, second up to T-1 parts. All right. Then we says that this matrix A satisfies the columns condition. And in the previous video, we have already seen that why this columns condition is necessary. So this video, we're gonna see the hard direction, why this columns condition implies that the AX is regular. So we will first build on several lemmas. Okay, so let me start with this formalism. So let A be a family of finite subsets of the set of positive integers, and we say A is homogeneous if n times x is in A for all positive integer n and x in A. So whenever you multiply positive integer, it's still in A. So you can think of this A as set of all solutions of homogeneous equations, homogeneous linear equations. Then when you have a solution, you multiply same number, then you still have solution, so it's homogeneous. And we say A is regular if for every R coloring of positive integers there exists one AR, there exists a monochromatic member in A. Okay, then we say it's regular. It's similar. So if A is a set of all solutions, then this is what we want. We want to have monochromatic solutions. All right. Now here's the first lemma. So let A be a homogeneous regular family of subsets, of finite subsets. Of N, let M be a fixed number if chi is an R coloring of n, then there exists a subset A in A and some number, positive number D, such that A plus lambda D for all lambda less than or equal to M and all A in A have the same color. Right. So this means that, I mean, we had a similar lemma, did we? Yeah, I think, yeah, we may have a similar lemma. So whenever you have a regular family, actually you can extend it further, so that when you go near, when you have a regular, I mean, monochromatic set, even if you change each entry by a fixed by a small multiple of D, then you still have the same color, right? So I mean, D could be big, but all right. So here's the proof. So you have we define regular as follows, right? So for any R coloring induces a monochromatic member. But by the compactness principle, there exists an integer R such that any R coloring of the positive set of positive integers R induces a monochromatic set. In A, right? How do we do that? Well, we construct a hypergraph on the positive integers whose set of edges is A, and then you think of the chromatic number, and the chromatic number right? And then we had a theorem saying that chromatic number is big if and only if there's a finite induced subgraph whose chromatic number is big. Anyway, so that's that integers. There's some positive integers such that whenever we color this integers from 1 up to R by finite or many colors, you have monochromatic member. So that's because A is regular. Now let chi be an R coloring. Of N. Now, what we're gonna do is the following. We will define a new coloring, KAIST, be a coloring. Okay, number. I will fill in this blank. This coloring of N such that I want this property. KAIST of alpha is equal to KAIST of beta if and only if chi alpha is equal to chi beta, chi 2 alpha equals to chi 2 beta, chi 3 alpha is equal to chi 3 beta, up to chi r alpha is equal to chi r beta. All right. So in a sense, we want to encode all the colors of the multiples of alpha up to this r alpha as one color. So the number of colors we need is r to the r, small r to the large r. This many colors we can encode, right? That's the number of possible colors. Now let's define t to be m times r factorial. You will see why I chose this number. I mean, there are other choices. By the van der Waals theorem, there exists a monochromatic arithmetic progression of length twice t plus 1 under this new coloring KAIST. So what does that mean? That means thus there exist C and E such that KAIST of C plus lambda E, no, let's say mu, let's use mu, is constant for all mu less than or equal to t. Right? Just pick C as the middle one in the arithmetic progressions. Now consider chi as an R coloring of C, 2C, 3C, 4C, and let's say RC. Right? And then by what? By the van der Waals, no, not by van der Waals. Since A is regular, right, and homogeneous, there exists a set B in A such that B is a subset of R, and when I multiply C, then this is monochromatic under chi, right? I mean, chi is okay. Right. I mean, because I had a coloring chi. Now I think of another coloring of integers from 1 up to r based on the color of C, 2C, 3C as up to RC. Then since A is regular and homogeneous, there's a set B, so that, I mean, it's regular, so there's a set B, so that this color B is monochromatic under this color, which means that C times B is monochromatic. I don't know whether I need homogeneous here. Probably not, right? Oh, yeah, it is. And what I need is actually C times B is in A because this is homogeneous. All right. Now let Y be the least common multiple of all elements in B, and A is C times B, and this is in A because, yeah, maybe I will fix it. Let me delete this line. This is because A is homogeneous. All right, and D is going to be E times Y. Yeah, so I'm multiplying this least common multiple. Now I claim that A plus lambda D. So then for each A in A and lambda M, what's going to happen is, well, let me write A as the C times B, where B is in B. Then A plus lambda D, this is what we are aiming, right? We want to say that A plus lambda D is monochromatic. This is what? C times B plus lambda times E times Y. Right? But Y is the least common multiple of all elements in B. So in particular, this B divides Y. So B times C plus lambda E times Y over B. Now I didn't use a good number, but let me give a very crude thing. Well, I mean, I didn't have to choose this R factorial, but I mean, I don't need to choose LCM. I could have chosen the product of all elements in B. But anyway, Y over B is at most R factorial because it's less than or equal to the product of elements in B except this particular small b, right? So this means that lambda Y over B is at most m times R factorial, which is actually T. And that's how I chose T. I could have optimized a bit further, but why not? Right? And therefore, by the choice of this C and E, chi star of C plus lambda E Y over B is what? This is equal to chi star of C, right? No matter how like this mu is small, right? Mu is less than or equal to T, so therefore this is constant. So even if I put 0, it's gonna have same value. So this implies, and now I can multiply same number and it's gonna be still same. So chi of A plus lambda D is equal to chi of BC, which is A. This is true for each A in A and right. And since A is monochromatic, in chi, all of A plus lambda D for all A in A and lambda less than or equal to M have the same color. Okay, so that's the proof of the first lemma. Now let's do the second lemma. So again, we have a homogeneous family. A regular family of finite subsets of n. For every positive integer m and c, and every r coloring chi of n, there exists a in a and d positive d, such that now we want to extend it further. Such that a plus lambda d for all a in a and lambda at most m, and cd have the same color. So again, this is similar to one of the lemmas for Van der Waals theorem. We had a theorem saying that not only we have arithmetic progression having same color, but some multiple of the difference also have the same color. And this is analog. And the proof is similar. Okay? All right, how do we prove that? You may already guess that the proof will be by induction on R. All right, so by the compactness principle, from the induction hypothesis, I mean, we may assume, by the way, we may assume R is bigger than 1. If everybody has same color, then there's nothing to prove. By the induction hypothesis, there is some integer r such that any, let me say t, every r minus 1 coloring of t induces a pair, let's say, a in a and d positive, so that all of the a plus lambda d for a in a and lambda at most m and cd have the same color. Okay, maybe I should say for all m no, t depends on m and c, right? For all m and c, there is the t, right? All right, so that's what we get from the induction hypothesis. Right, so now let's start with the R coloring. Chi-Bian R coloring of the set of positive integers. By the previous lemma, right? So by this lemma, there exists A in the family A and D prime positive, such that all of A plus lambda D prime with A in A and lambda and most anything I want, right? Any fixed constant I want. So I'm going to put T times M, right? Have the same color. So if for some mu and most T, mu times CD prime have the same color as well, then we can set D prime, no, D as mu times D prime, and then R of A times lambda D for all A in A and lambda in most M will have and CD will have the same color, right? Because lambda D is equal to lambda mu D prime, but mu is small, so therefore it still lies within this arithmetic progression, which is monochromatic. Therefore, we may assume mu times C times D prime for all mu and most T avoids this particular color, right? So then the number of colors used by those numbers are R minus 1. So let chi prime be an R minus 1 coloring of integers from 1 up to T defined by chi prime alpha is equal to chi of C times alpha, C times alpha, CD times alpha, CD prime times alpha, right? And this is well defined, and it avoids one color because if I put alpha to be 1 up to T, then CD times alpha will avoid that particular color, so the number of colors used is R minus 1. Right? So, but then by induction hypothesis, and the assumption on T, okay, and the assumption on T, there exists B in A and D double prime positive, such that B plus lambda D double prime is always in this range for all lambda and most M and B in B, and all of B plus lambda D double prime and CD double prime have the same color under this new color in chi prime. Okay, why is this useful? Right, so let A be the set CD prime times B, and D with the CD prime D double prime. Then for all A in A is actually CD prime times B for some B in B, right? And then for all lambda most M, the color of A plus lambda D is equal to color of CD prime B plus lambda C. Oh yeah, what is D? And let D be, oh yeah, D is there. CD prime D double prime, right? And this is equal to chi prime of, now we divide, oh, maybe I should, yeah, this is okay. So this is common, and when I ignore that, then you have the chi prime, so B plus lambda D double prime, and by induction hypothesis, this is equal to chi prime of B. And also it's equal to chi prime of CD double prime. And this, right? And this is equal to chi of A, and this is equal to chi of, what is it? C squared D prime D double prime, which is equal to chi of CD, right? So that means all of A plus lambda D and chi CD will have the same color. So we are done. All right, so we have proved that two lemmas. Now we're gonna define something called the Mpc set. So for positive integers, Mpc, a set S of positive integers is called an Mpc set if there exists a sequence y, y1, y2, ym plus 1 of positive integers such that S is equal to, so let me write it as this notation, so equal to D of Mpc semicolon y. This is defined as the union of the following. So union of say from 1 up to m plus 1 and cyz plus lambda I yi, where I is from j plus 1 up to m plus 1. And here lambda I is at most p for all I. Right, so that's the what's called the Mpc set. So set is Mpc set if there exists a sequence y1 up to yn plus 1 such that your set is equal to this. And without example, maybe it's not really easy to see what this is. So for instance, right, so okay, let me rewrite the definition of Mpc set. So what is this? This is equal to like a union of the following. So when j is 1, it's going to be cy1 plus lambda 2 y2 lambda 3 y3 up to lambda m plus 1 ym plus 1. Numbers, all of numbers like that, where lambda I is at most p. And then you have numbers like cy2 plus lambda 3 y3 lambda m plus 1 ym plus 1, where lambda I is still at most p. And then you have numbers like cy3 up to lambda m plus 1 ym plus 1. And then the last one is cym plus 1. This is just one number, right? So for instance, one example is, let's say cy1 plus lambda 2 y2. Okay, let me replace y1 y2 by something. C1, okay, 10 lambda 2. The set of all numbers like this, where lambda 2 is at most 10, union C, 10C, where there's nothing. This is one instance of the what is m? M is 1 and p is 10 and c is, oh, I didn't put c, let's say 5. Right? So 5, where the sequence itself is right 1 and 10. All right, so that's the Mpc set. So it's a set of positive integers. So it's, in a sense, it's more in a concept. It is a concept that generalizes the arithmetic progressions, right? So when you have a m to be 1, if m is 1, then this is really arithmetic progressions, except you also want constant times this thing, c times d is also have the same color. But this was consequence of van der Waals theorem, right? So you can find arithmetic progression and c times this difference to be also have the same color with that arithmetic progressions. Where did we prove it? I'm trying to find, yeah, before the I forgot where it is. I mean, it's related to the homework problem, possibly, yeah. All right, never mind. So the case when m is 1 is exactly m is slight strengthening of van der Waals theorem. Now here's a proposition. Let me say proposition. For all positive integers Mpc R, if the set of positive integers is R colored, then there exists a monochromatic Mpc set S. Oh, by the way, when you define Y, note that all these Yi's are positive, right? Because these are positive integers. Otherwise, it's trivial. You can take all Y's to be 0, and then any single, then it will be too trivial. All right, so the proof is induction on M. If M is 1, then an Mpc set is, so we have seen already, it's like C1 plus C1Y1 or C2Y, no, not C2, lambda 2y2, where lambda 2 is at most P union cy2 for some y1 and y2. And oh, actually, yeah, this one, let me when we proved the simpler version of Rados theorem, we had such a lemma. All right, so it's near here. Oh yeah, here it is. Here we go. Yeah, so this is the lemma that I'm talking about. All right, so what we do is, so by the lemma based on the van der Waals theorem, in section what's the number, 11.2, right? There's a monochromatic 1pc set, right? So there is the choice y1 and y2, such that this is monochromatic. So if m is 1, then it's trivial. Oh, what is C1? I should I mean, it's not trivial, but you can apply that. Oh, but some of you may wonder what happens. Why do we have a, here you have, in this form you have 1 times A, right? Here you have a C times Y1, C times Y2. How do we deduce this set from here? Here you only have A, and SD. So if I put S to be C, I only get A plus something, and then CD. Here you have I mean, if this is 1, then this is exactly the previous lemma, but now here we have C. How do we obtain such a thing? Well, apply the lemma to a coloring So new coloring chi prime, where chi prime of alpha is equal to chi of C alpha. So I'm only going to consider coloring of the multiple of C and then take S to be 1. Right? So try to find the arithmetic progression inside the multiple of C. And then I will give you what we want. All right. Yeah. So now we may assume m is bigger than 1. Let's go back. Right. Now we assume m is bigger than 1. So then by induction, hypothesis, there exists a right. Well, let me do this way. So let A be the set of all m-1 PC sets. And then by the induction hypothesis, A is regular, right? Because that's what we are trying to prove. No matter how I color, there is a monochromatic Mpc set. And clearly A is homogeneous, right? If somebody is an Mpc set, then you multiply same number, it's still Mpc set. So by the previous lemma, now let's see the meaning of the previous lemma. From an Mpc set, and from an m-1 PC set, A plus lambda D and CD for all A in A. Oh yeah, so there exists a monochromatic there exists A in A and D this is positive, such that A plus lambda D for all A and lambda in most M. Oh yeah, instead of M I will take a P, and CD have the same color. Then we take ym plus 1 as D, right? So that means this. Then what we have is the union of all these numbers are clearly is an Mpc set, right? Because think of D as ym plus 1, right? So you are multiplying this lambda. Yeah, so lambda is going to be lambda m plus 1. right? Then all of them and this have the same color. So we're gonna have an Mpc set. All right. So that's the proof. So this build up for all these lemmas, and then this set, Mpc set. So we are adding this last column. All right. So now how we gonna prove the Rados theorem? Finally. The backward direction. Right. So let A be a matrix satisfying the columns condition, right? So C1, C2, Cn be the column vectors of A, and I1, I2, IT be the partition of the column vectors, but partition of the integers from 1 up to n, satisfying the columns condition. So what does that mean? That means I know that Ci in I1 is 0 and C2, no, Ci, some of the Ci in I2 is in the span of vectors in I1 and continue, right? Now, what do we see here? So, for instance, sum of Ci in I2 is a linear combination of vectors in Cj, where j is in I1, right? So this means that when you have a matrix A, and if I put like 1, 1, 1 for the vectors, right? So this is location for rows for I2, and this is rows for I1, and this is 0, right? Let me rearrange. So these are rows for I1 and rows for I2, let's say. Right, so here you have a rows for I1, I2, and then this linear equation says that there's some rational values here, and I can put 1, 1, 1 here, and that will, and then put 0 here. Then when I multiply that to A, then we get 0. All right. So in other words, we have a vector G we have a rational vectors G1, G2 up to GT in qt, not qt, qn, such that a times gi is 0, gj for j in t, and gji is 0, 1 if I is in ij, right? And 0 if I is in I j prime and j prime is bigger than j, and some other number, any if I is in ij and ij prime, j prime is smaller than j, right? So this is just description of these linear combinations. So let us choose a large integer c such that czi is now the rational integer vector. Why not? I mean, you can take the common denominator. I mean, look at all denominators and then multiply all of them. Then take capital GI as a c times GI. All right. Now, what does that mean? That means that now we have a parametric solution of ax is equal to 0. Like take x is equal to sum of yi gi, right? Because note that a times gi is 0 for oi. So ax is 0. So let p be the largest absolute value of the entries in G1, G2, GT. Then there is a monochromatic Mpc set S, which will give the monochromatic solution, right? Because when you have a monochromatic Mpc set, then you put over here, right? The sequence y1 up to yn plus 1 will give you such a thing. Am I doing all right? Yeah, but what is m? What is m? So I should replace m with something else, right? T minus 1. Yeah, so that looks like the solution, right? So once we have a monochromatic T minus 1 PC sets, then each of them will look like C plus, oh, what is C? I can take C to be 1, right? So Y1 oh, this is the other way. Okay. Why is this the end of the proof? So when you have t minus 1 p1 set, then we will have is something like y1 right? So y1 plus lambda 2 Yes, so y1 plus lambda 2 y2 lambda t yt, and the y2 plus lambda 3 y3 up to lambda t yt. Okay, let me until you have yt. All of them have the same color. No matter how I. But are you happy with this? Well, the thing is, let's look at GI. So G1 is something like 1 1 1 0 0 0 0, right? And G2 is something like some numbers and then 1 1 1 and then anything. G3 is something like anything and then 1 1 1. Oh no, anything 1 1 1 and 0. All right, so that's what's happening. So if I had a Mpc set, then what's going to happen? Right. So what we know is x is equal to this linear combination of yi ci. Then what is x? This is equal to x1 x2 up to xn. Right. So now let's look at the xi, right? So for instance, x1, right? So x1 is given by some y1 plus some star y2, some star y3, some star yt, and x2, and where star means some entry in GI. X2 is similar, so y1 plus some star y2, star y3, star yt. and you do it until I is in I1. So this is for I1, and then once you start with I2, then you have X something. Now then you no longer has anything from G1, right? Then it's gonna be Y2 plus star Y3 star Y4 up to star YT, and you continue. That's until I2. And then when you have hit the I3, then it's gonna be, this is equal to Y3 plus star Y4 up to YT, right? And all these star entries are absolute value and most what? And most P. Oops. Right. So all these values have absolute value and most P. So and this is a formula for general solution of this thing. Now, since we have a T minus 1 P 1 set, right? So since we have T minus 1 P 1 set, which is monochromatic, so that will generate a set where all these things are inside the same set, right? Same monochromatic set. So that's why it has the same colors. And this idea is, yeah, so this is the end of the proof. All right.